Okay, so now we're going to look at how we can stop climate change and achieve what we call drawdown. Stopping climate change is necessary if we want to have a better future, because everything we do is connected back to climate change. Our water, our food, our air, our health, our security, our economy are all connected to what happens to weather and climate. So if we don't fix climate change, all the other things we care about in the future are going to be a lot harder. So we need to address climate change in order to have a better future with a prosperous economy, with resilience, equity, justice, and creativity. All the things we want demand that we address climate change. And that's what we're about. I work for something called Project Drawdown, which is the world's leading resource for climate solutions. We focus on the science we need to know to address climate change and then share it with the world. But why do we use that word drawdown? What does that even mean? Well, drawdown refers to a point in time in the future, and it refers to the greenhouse gas levels in the atmosphere. Now, I remember I told you in the last unit, greenhouse gases have been building up in the atmosphere. Here we are today at the 2020 levels. But then we can choose what happens next. On the path we're on now, we'll just continue to build up these gases, which will just warm the planet more, making the problem worse. But we don't have to do that. We can bend the curve. Bending the curve on climate change means reversing the curve of growing greenhouse gases. And when we hit this point, the little blue dot here, that's the moment of drawdown. That's the moment when greenhouse gases stop climbing and they begin to go back down again into a healthier place. So drawdown is the moment in the future when greenhouse gas levels stabilize and stop climbing, and then they start to steadily decline. And that's when we begin to stop climate change. At Project Drawdown, our job is to get the world to drawdown as quickly, safely, and equitably as possible. So how do we get there? Well, first, we're going to have to learn a little bit of science. It won't be too hard, but it's the stuff we really do need to know to kind of get forward on climate solutions. So first of all, what are greenhouse gases? Well, you've heard a little bit about this before, I'm sure. You know that greenhouse gases kind of let in the sun's heat and they trap the Earth's heat as Earth is radiating out into outer space. So essentially they trap heat. And the more gases means the more heat. And that's why the planet's warming up. Pretty simple. There's a little bit more to it. It turns out that Earth already had greenhouse gases before we came along. There were natural greenhouse gases like water vapor, a little bit of carbon dioxide, and a few other things that have been there for millions, if not billions, of years of Earth history. But then we've got these things we call anthropogenic greenhouse gases, or human-caused greenhouse gases that we've been adding on top of that. And those include more carbon dioxide than was there before, more methane, more nitrous oxide. We've added chemicals that weren't even in the atmosphere before, like fluorinated gases, so-called chlorofluorocarbons, hydrofluorocarbons, and so on, and many other gases that are impacting our climate. And we can actually see how they've been rising over the last 100, 200 years. And especially in the last few decades, we have changed the nature of Earth's atmosphere and added a human greenhouse effect on top of natural greenhouse effect. And that's where we're getting into trouble. So what do these do? It's actually really simple physics. The idea is greenhouse gases are transparent. They let solar radiation, visible light, what we can see, right through them, like just a window. You can see right through it. But in infrared radiation, which you and I can't see, it is opaque. The infrared radiation is what Earth gives off to the rest of the universe, and so it can trap that heat in the atmosphere. It kind of works like this. Imagine a version of Earth with no atmosphere at all, like the moon. It would absorb the sun's radiation and warm up. The sun's heating the ground, and the ground would warm up. The ground, just obeying the laws of physics, would also give off heat or infrared radiation back to the rest of the universe, out to outer space. And without an atmosphere, this is what it would look like. The sun's heat comes in, Earth heat goes out, and they'd be in perfect balance, and we'd be at a temperature that would be accordingly in balance with that. But now let's add an atmosphere, a natural atmosphere. So we have what was the natural greenhouse effect. The idea is, as Earth is radiating its heat out into outer space, some of it would be absorbed by the air above it, and some of that would then be re-radiated back down towards the Earth's surface. That has the effect of making the Earth's surface a little bit warmer and the upper atmosphere a little bit colder. And that's exactly what Earth has had, and so are mainly all the other planets. Venus, Mars, and others also have a greenhouse effect kind of like that. But then humans come along and we add some more of those gases to the atmosphere. It'd be like adding another blanket on your bed in the wintertime. It traps more heat and keeps you toastier, a little bit warmer, and so on. And so this enhanced greenhouse effect traps a little bit more heat, radiates a little bit more down, and it warms the surface even more. And so far, we've warmed the planet about 1 degree Celsius. That doesn't sound like a lot, but think about it. During the last ice age, the planet as a whole was only 3 degrees colder than normal, and it was a totally different planet. This place was under about a mile of ice, in fact. We've warmed the planet in the other direction by about 1 degree so far, and we're going to keep going. If we keep going to another 2, 3, or 4 degrees, that could be a world we wouldn't even recognize. It would be very, very dangerous for our civilization. So where do these gases come from? Well, I'm sure you've already heard that a lot of them come from burning fossil fuels, right? Burning oil and natural gas and coal and petroleum substitutes and all these things that we have. And that is part of the story. Burning fossil fuels does create CO2, and that causes about 62% of the warming we see on the planet today. So if you forget about everything else, fossil fuels cause more than half of climate change. But that's not all. It turns out that CO2 is also produced by a few other things, including chemistry. In fact, a lot of our industrial processes, especially making cement, releases CO2 into the atmosphere without burning anything at all. It's just kind of industrial chemistry. We also release a lot of CO2 into the atmosphere by burning down trees and deforestation. This green area shows you how much CO2 is caused by burning down forest, which is kind of like burning coal. Coal's dead, trees are alive, but they're both made out of carbon. And you burn them in our atmosphere, you will make carbon dioxide either way. Then we have our next greenhouse gas of methane. Methane is produced by a whole bunch of different things, but the two big sources are agriculture and industry. In agriculture, which is about 2/3 of this methane emissions, is caused largely from cattle. And you've heard all the jokes before, I'm sure, about cow farts. Turns out that's not even true. Cows actually burp methane. They don't fart methane any more than other animals. The other third of this methane comes from industry, especially mining natural gas. Gas wells, fracking, gas pipelines, even coal mines release methane as well. So we have to think about energy and industry and agriculture to look at methane. Then we've got this stuff called nitrous oxide, which a lot of people don't even think about, but it's a big part of our climate change equation. And nitrous oxide, some of that comes from industry, but again, a lot of it comes from agriculture, especially using too much fertilizer or too much manure on our farmers' fields. And finally, we have F gases, or fluorinated gases, which are chemicals we use as refrigerants and sometimes as insulators in industrial processes. And those refrigerants, like chlorofluorocarbons and hydrofluorocarbons, are rising dramatically, and that's why we have to pay attention to this. So putting all those gases together, we emit about 52 gigatons of the equivalent of carbon dioxide into the atmosphere each year. What the heck is a gigaton? It's just a fancy word for a billion metric tons. So we emit 52 billion metric tons of pollution into the atmosphere every year. But there are only 7.5 billion of us. So on average, we're emitting many, many tons of pollution per person into the atmosphere. That's a huge amount. And we're going to talk more about that and how we can cut that down. Another thing we have to notice is that each of these gases works a little bit differently. Some gases trap more heat than others, like methane and nitrous oxide, and those fluorinated gases trap way more heat molecule for molecule than CO2 does. But some gases last longer in the atmosphere than others too, and we got to take that into account. Like methane, we emit today, most of it will be gone within 10 to 20 years. CO2 we emit today will be in the air for centuries and centuries to come. So we have to look at the strength and lifetime of these different gases. In particular, when we think about methane, methane again is that part of the wedge of our whole diagram of greenhouse gases. If we look at the impact of today's emissions on climate for the next 100 years, Methane will cause about 16% of that warming over a 100-year period. But if we look at the next 20 years instead, the role of methane doubles and becomes 32%. So it turns out in the near term, our climate changes are going to be caused by mainly methane and other gases, but in the long term, they're going to be dominated by things like CO2. So which gas we focus on depends a little bit on what time period of climate change you're really most concerned about. We have to look at all of them. Now that we understand what greenhouse gases are and kind of how they work, we're going to look at what regulates the level of those gases in the atmosphere, what makes them go up and what makes them go down. To do this, sometimes it's helpful to think of a bathtub. But imagine a bathtub which we can fill and empty with water. We do that every day, right? Pretty simple. When we add water to the bathtub by turning on the faucet, we scientists call that a source. It's a source of water, and it levels up the water in the bathtub. We can also remove water by opening up the drain, and scientists call that a sink. You'll hear that word a lot about sinks of greenhouse gases. The difference between the sources and the sinks determines whether the water goes up or the water goes down. Sources add and make the water go up. Sinks remove and makes the water go down. Now, if you have a bathtub with the faucet on and the drain open, we have an interesting picture. If the sources are bigger than the sinks, the water level will still go up. But if the drain, the sink, is bigger than the faucet, the source, the water levels will go back down again. So let's take that and apply it to Earth's atmosphere. Well, Earth's atmosphere is basically a big bathtub in the sky. We can fill it with pollution and greenhouse gases, these sources of greenhouse gases, which is largely due to us. And then we have sinks of greenhouse gases, things that pull that pollution out of the sky and put it someplace else. We have sinks on this planet of greenhouse gases, primarily in plants, on land, but also in the oceans. So here's the picture. We put pollution in the atmosphere, nature pulls it out in forests and in oceans. Now, right now, our sources of pollution, the stuff we're putting in the atmosphere, is much bigger than what nature can take out. And that's why the levels are going up. But what if we reduced our pollution? What if we brought it down by a half or so? Well, then maybe nature could kind of keep up with it and pull as much pollution out of the atmosphere as we're putting in. If that were to happen, we would hit that moment of drawdown and we'd stabilize CO2 levels and they'd stay flat. But we can go farther and actually reduce our pollution down to zero and pull more carbon and other stuff out of the atmosphere and actually have greenhouse gases decline and stop climate change and begin to reverse in the long term the damage we've done. So this balance between sources and sinks is what will determine the future of our planet and our climate. Now let's look at the numbers. In today's atmosphere, we see that we actually have about 6 major sources of greenhouse gas pollution. We'll go into them later, but you see electricity and food, industry, transportation, buildings, and other stuff. Then we have nature, which on land and in the oceans pull out a total of about 41% of those greenhouse gases, primarily the carbon dioxide part. And that leaves behind 59% of those greenhouse gases in the atmosphere, building up year over year over year. So to achieve drawdown, to get them to reverse and bend the curve back down, we've got to work on both sides of this equation. We can work on the sources and bring them down to zero, kind of turning off that faucet over the coming decades, so there's no pollution there at all. And we can also work with the sinks of carbon, starting with the natural ones that already exist, and make sure they can continue to pull that stuff out of the sky. So the idea of getting to drawdown actually will be based on 3 big principles, and these are important. The first thing we've got to do, and we always need to begin here, is reduce the problem before it even starts. Let's stop pollution before it even gets in the atmosphere so it doesn't cause any problems at all. And that means bringing these emissions down to zero. So we're going to have to zoom in and look at what causes these emissions, what's in the economy, what can we do about it in all of these different sectors, from electricity to industry to agriculture and beyond. And if we do that, we can cause a big reduction in these things and eventually bring them down to zero. So job number 1, stop pollution, bring it to zero. Job number 2 will be working over in the nature space, basically supporting nature's carbon cycle and maybe even adding to it. in the form of sinks. That's the right-hand side of this diagram. We'll have to zoom in here and look on land and oceans about what controls their ability to take up carbon and how can we support that and maybe even augment it, making it stronger in the future. So we've looked at the left-hand side and the right-hand side of that big picture, the sources, the sinks, and we know what to do. But there's a third area we've got to talk about too, and we'll get into this later, is about how, as we improve society, we can do things that aren't about climate change. They're things we should do anyway. But when we improve equality and equity and justice around the world, there are things we do there that actually have major secondary climate benefits. So we might get a twofer of improving human rights and equality and contributing to climate solutions. So working together, reducing pollution, supporting nature, and improving society are the three pillars of our climate solution space. Building on these three pillars and pulling them together all at the same time, we actually have all we need to address climate change in the coming decades. And this is going to be our job over the next few units of this course.